Here's a fact that may interest you. Pluto's orbit has a radius of 7.5 billion kilometers. And if you knew the value of pi to 15 places of the decimal, you could calculate the circumference of Pluto's orbit to within 2 centimeters of its correct value. Here's another fact. Not only is Pluto much smaller than our moon, it is also much lighter as well, with an estimated mass less than a sixth of the moon's. And since all good things happen in threes, here's a third fact for you. Pluto travels around the sun so slowly, it hasn't even completed 2 full orbits since Babur established the Mughal Empire in India. These facts relate to 3 fundamental quantities that we work with all the time in physics: length, mass, and time. Let's see how we measure them. We define length as the separation between 2 points. We can also define length as the magnitude of the extent of the path that connects 2 points. The standard unit of length is meter, noted by the symbol small m. A more common unit derived from the standard unit is kilometer, where kilo stands for 1000. Next comes mass. As little kids, we learned that the mass of an object is the amount of matter inside an object. While true, this was not a very useful definition. Newton had a better idea. He defined mass as the ability of an object to resist acceleration. He also gave this property a new name, inertia, which is why mass is also called inertial mass. But what does it mean to resist acceleration? Think of it this way. We know that acceleration is a change in speed. Take a bowling ball that's sitting still and try to push it across a table. You will notice that you need to put in some substantial effort. Try the same with a football of roughly the same size and you notice it's a lot easier. On the other hand, stopping a bowling ball, which is already moving, is also much harder than stopping a football moving at the same speed. So it is clear that a bowling ball resists a change in speed, whether it is an increase or a decrease, more than a football. This is inertia, and this gives us a very useful definition of mass. The standard unit of mass is kilogram or 1000 grams. In real life, we also use multiples of this unit, like the quintal, which is 100 kilograms, or the ton, which is 1000 kilograms. And that brings us to time. Time is a lot trickier to define compared to the other 2 physical quantities that we have seen. Time cannot be touched, it cannot be seen. It can only be sensed as a separation between 2 events and can be traveled in only one direction. The standard unit of time is second. This unit is usually too small to be used in daily life, so its multiple units, that is minute and hour, are used more commonly. So what is the range over which these units vary? Well, the size of a single nucleus can be 100th trillionth of a meter, while the width of the observable universe is 100 trillion meters. The mass of a single electron is less than the 1000th of a trillionth of a kilogram, while the mass of the universe is estimated at more than 10,000 trillion kilograms. Now that we have understood the basics of how these fundamental quantities are measured, let's take a look at some interesting techniques developed to measure things which are really large and really small.
Manorama Horizon. Learning made simple.